Jack manages the UK and Scandinavian business district within Regenesis Europe. For those of you who are not familiar, Regenesis offers a suite of technologies and services to treat a wide range of contaminants, including petroleum hydrocarbons and chlorinated solvents via enhanced bioremediation, chemical oxidation, desorption, and metal immobilization. Jack has over 10 years experience within the remediation industry, and most recently has successfully implemented the first injection of plume stop to effectively stabilize a PFAS plume in the EU. During today's webinar, Jack will explain the complexities of an industrial site in Scotland and the application of a combined biostimulation and bioaugmentation treatment that was designed to remediate this site. As always, there will be a time for a Q&A session after the presentation, so please submit your questions in the chat box on the bottom right corner of your screen at any point during this webinar. Thanks for logging in. Jack, over to you.
Thank you very much. My name is Jack Shaw. I'm the UK and Scandinavian District Manager for Regenesis. And I'm here to present a site where we injected a series of electron donors and also an inoculum to successfully remediate DNAPL concentrations of both chlorinated ethenes and ethanes while a site remained commercially active. So what I'm going to do, I'm going to take you through a very brief introduction to Regenesis. I'll then talk about what chlorinated solvents are, where they can be found, and the problems that are associated with them. We'll then do a brief site overview of the site that we remediated. We'll look at previous remediation activity. We were not the first choice on this site. Then the problems that particular remediation method had, and then how we overcame them. We'll then look at a brief pilot that we did on this site, less to prove the efficacy of the technology, but more to ensure that the chosen application method could get to the required depths. I'll then walk you through the two technologies that we chose, 3DME, 3D microemulsion. This is our electron donor, and then BDI. This is our microbe inoculum. And then finally, the results and conclusions. And that graph that you can see there on your right, those were the results that we yielded post full-scale injection. So as a company, Regenesis, briefly, we've been around since 1994. Before Regenesis, nobody injected any proprietary reagents into the ground. We were the first company to research, develop, and commercialize these sorts of injectable reagents. Since then, we've released a whole bunch of different technologies, ranging from controlled release electron acceptors, such as ORC for hydrocarbon remediation, very safe to use in situ chemical oxidants, such as Regenox, which is used probably every working day in the UK, as well as appropriately soluble electron donors, such as 3DME that we'll cover in this bio-dechlorinoculum. As well as more recently a series of liquid activated carbons and colloidal zero-valent ion products. But firstly, on to chlorinated solvents, sort of what they are and the problems associated with them. So typically with chlorinated solvents in the environment, you come across two types, chlorinated alkanes and chlorinated alkenes, both of which we came across on this site. Chlorinated ethenes, TCA and TCA, less common. And then the more common types that you would come across typically in a dry cleaner or a metals manufacturer, chlorinated alkenes, so these such as PCE and TCE, and the daughter products that that are produced through natural attenuation, DCE and vinyl chloride. Now, when you have a commingled plume of both chlorinated alkanes and alkenes, and you're looking to enhance the rate of natural attenuation, what you can sometimes find is the chlorinated alkenes, so PCE and TCE, will degrade fairly readily, and then you would have TCA where you would see some stool, and essentially the reason for that is the microbes prefer to break down. It's an easier meal for them to digest. These are the PCE and TCE. So often there is a need to do some form of bioaugmentation to ensure that you don't see TCA stool. In terms of some of the physical characteristics of chlorinated solvents, they are DNAPL, so dense non-aqueous phase liquids. When they are released into the environment through a spill, they will percolate through the unsaturated zone, through the vadose zone, and then hit your groundwater table and continue to sink. As they percolate and sink through the environment, they will leave ganglia of DNAPL as they move vertically through the strata. They will sometimes pool on less permeable strata and then diffuse into clays and the secondary porosity of bedrock, and continue to sink until they hit a truly impermeable zone. This makes them very difficult when it makes site investigation and delineation very difficult. It's often very hard to work out exactly where the source of that contamination is. Now, when it comes to remediating these compounds, there's an added problem, because as they migrate through the subsurface, they will start to diffuse into low permeability zones. So they'll initially transport through high permeability zones, high K zones, such as sand lenses, for example, through advection, and then they will steadily diffuse into your lower permeability zones. And it's that diffusion into those lower K zones that can make them progressively harder to recover using physical remediation techniques. And it's also a problem, particularly if you're looking to get down to very low remediation target levels for the site, which often you are required to do, sort of maybe less so than you are for petroleum hydrocarbons. Consequently, there are a range of different techniques that you can use to address chlorinated solvents in situ. What we in Regenesis tend to favor is biological treatment. This graph just briefly shows treatment efficiency and contaminant concentrations. Where you do have chlorinated solvent sites and you have measurable DNAPL, you can actually measure the DNAPL in your well. The most efficient and appropriate thing for you to do would be to try and recover that as much as possible. I've looked at some 500 chlorinated solvent sites in my time, and I could say I can think of 4 off the top of my head where we were actually able to find these DNAPL sources. What's often the case is that you are looking at your groundwater results. They're above saturation limit that would indicate there is DNAPL, but it's not measurable. So physical treatment is an option, but it often isn't appropriate. Chemical oxidation is also something you can do, particularly if you are short on time and you're looking for rapid mass reduction in a very short period of time. The thing with chemical oxidation is that it relies on contact. The oxidant and the contaminant need to make contact with each other in order for that chemical oxidation reaction to occur. Particularly if you're looking to hit low groundwater targets, the efficacy, the efficiency of that chemical oxidation reaction will start to drop off as those concentration levels drop. Conversely, here with biological remediation, you can absolutely take DNAPL levels of chlorinated solvents, and through the addition of an appropriately soluble electron donor, and I'll talk about that in a little bit more detail as this presentation goes on, are able to successfully reduce significant proportions of contaminant mass to lower dissolved phase concentrations to levels where they no longer present a risk. In terms of where you can find these, where you find chlorinated solvents, dry cleaners, often where they've used PERC or PCE to clean clothes, or one type of site. Often, though, you find them on large industrial manufacturing sites, pharmaceutical sites, and chemical works, where they've been used in the degreasing process, and often on a lot of large Department of Defense sites as well. However, this case study that I'm going to talk about today, this site in Scotland, was a metal plating works. So it was a commercial industrial site. The characteristics of this site was that there was about a 1,500 square meter plume of TCE and TCA across this site. The geology comprised of clays overlaid by sands, and then beneath you had a granite bedrock. There were sort of exceptionally high levels of both TCE and TCA on this site. So we had about 20 milligrams per liter TCA at the peak, and then 33 milligrams per litre of TCE across most of the area. If we averaged that out, it still averaged at about 11 milligrams per litre, which are very high concentrations for chlorinated solvents. In terms of impact thickness, so we were dealing with a treatment thickness of between 1 and 9 meters below ground level. Groundwater came in at 2.5 meters, and as I said, this geology, fairly heterogeneous, so we were dealing with glacial till and clay, underlaid by some coarse sands, and then finally a granite bedrock. What was interesting on this site was that the remediation of this site wasn't driven from a regulatory point of view. There was no risk to controlled waters or human health. Rather, the remediation driver was contractual. So what had happened is an American corporation had sold this site to a UK company. A condition of that sale was that the American company had to remediate and reduce the levels of chlorinated solvents in the groundwater beneath the site by 75%, and then to see no rebound within a 12-month period. So that was the remediation driver. That was the goal. Now, on this site, because it was commercially active, there were a number of challenges that we needed to overcome when developing a remediation strategy. It was commercially active. Most of the contamination was recorded within a large yard area that had to be open and operational about 14 hours a day. Lots of deliveries, lots of various plant being stored in this yard area, and we needed access to that. But equally, because the now site owner was under no obligation to sort of accommodate that remediation. That's something that the American parent company needed to execute. It meant that we could have absolutely no impact on their commercial operations. So actually, a lot of our work was undertaken over weekends and over nights to make sure that there was no impact to the ongoing site operations. Initially, though, before we in Regenesis got involved, a different remediation strategy was deployed. It was a physical remediation strategy comprising a dual and multi-phase vacuum extraction system. It was installed across most of that yard area to recover as much of the DNAPL as possible. And it did a fairly good job. You can see that initially there was some significant recovery through this treatment system, but it did run for a period of 3 years. And what they found is that when this system was switched off, they saw significant rebound occur during these periods of downtime. And subsequently, because there was this rebound, it didn't meet one of the contractual requirements. So what was decided was that further investigation was needed to take place. And one of the reasons for that is that they wanted to understand if the rebound that was being recorded was down to back diffusion. Now, there's two terms that I'd like to define before we kind of go into the details of back diffusion. One is advective aquifer remediation, so remediation techniques that rely on advection, and then diffusive aquifer remediation. We in Regenesis, because we inject products into the ground, we rely on both. We rely on advective distribution of a substrate and then subsequent diffusion of our electron, a donor in this case, or an acceptor to distribute in the aquifer. What these terms mean, so advection is, as I say, the primary mechanism for physical treatment systems. It is the primary mechanism for soil vapor extraction, dual phase vapor extraction. Advection is a mass flow phenomenon, so it is the movement of groundwater with contaminants, or the movement of air with contaminants within it. It's dependent primarily on the piezometric gradient, so Darcy's law, and matrix permeability, and to a degree the retardation factor that is imposed by any natural organic matter. And as I say, it's the basis of most in situ remediation methods. So pump and treat systems, for example, they pull out water from the ground that has contaminants within it, pass it through a treatment system, and then what is eluted out the other side of that treatment system is clean and then discharges to sewer. But it does rely on that recovery of impacted groundwater with the contaminants within it to then pass through a treatment system. Diffusion is different. So diffusion depends on concentration gradients. It's a molecular dispersion phenomenon. So it is the movement of contaminants in groundwater. It is not the movement of the groundwater itself. So as I say, concentration gradients, it depends on Flick's law. Concentration gradients are created, and then you get the diffusion of a compound across that concentration gradient. Crucially, it's not dependent on matrix permeability. All we need is for that matrix to be porous, and clays are porous, so you can get good diffusion through clay substrates. So advection is the movement of groundwater containing chemicals, whereas diffusion is the movement of chemicals within the groundwater. So that's two key points. So what we in Regenesis did here is we injected something, an electron donor called 3-DME, into the subsurface. That initial force of injection forced it into the subsurface, so that's the advective distribution. And then once it's in the subsurface, you then get this steady diffusion of hydrogen down concentration gradients that allow it to permeate into the matrix. In terms of what happens, is what was happening from a model point of view with this SVE system. They had this initial advancement of this contaminant plume. So here I've simplified things a bit. So it's advancing through a sandy seam. And as it's migrated through that sand, it steadily then diffuses into the clay because there's a concentration gradient. The thing is, when that dual phase extraction system is turned on, it preferentially recovers the contaminant mass within the more permeable strata, and then it creates a concentration gradient. So Flick's law says that you get diffusion, and it's that back diffusion that then causes the contaminant levels then to rise. And essentially this is what was going on this site. So you had this clayey overburden. The SVE system was turned on and did a great job at remediating the more permeable sands. But then you had this secondary source of chlorinated solvents from above, from this clay layer, that was then steadily diffusing into this sandy gravel and then causing rebound of chlorinated solvents. And you can see this in the graph where once the system switched off, you then start to get contaminant levels peak again. So as a result of this, the consultant that we were working with, Rambol, did further investigation to better understand where the contaminant mass was located on the site. In Regenesis, not only do we do research and development of these different injectable substrates, we also provide you with bespoke designs for each of your sites. And particularly when you're dealing with a chlorinated solvent plume, we actually find MIP surveys incredibly useful because we can get a really high resolution picture of the chlorinated solvent plume to ensure that when we come up with a design, we can be much more targeted in our approach. So it's a very useful tool for us. What they found here was that actually most of the contaminant mass, while it was in the shallower horizons, was mainly concentrated between 7 to 8 meters below ground level. And then at 9 meters, there was a sort of dip in the granite bedrock, and it was also pooling in that direction. So based on this information, the remediation strategy was revised to include enhanced natural attenuation, or otherwise known as enhanced reductive dechlorination, where we added an electron donor along with an inoculum to enhance the reductive dechlorination process. Now, the reductive dechlorination process, so this is just how microbes break down, how native microbes break down chlorinated solvents in situ. Essentially, you add an electron donor, so in this case 3-DME, and that's a source of hydrogen. That hydrogen is the electron donor. You have a group of microbes, such as D. halichoides, broadly known as D. halobacter, dechlorinating microbial consortia, that take the hydrogen atom, swap it out for a chlorine atom, and that exchange releases energy, which is the energy that the microbe needs to live. and then you reduce these chlorinated solvents in situ. So with PCE, you snap off a hydrogen atom, exchange it for a chlorine atom, and you end up with TCE. Same thing happens again. TCE gets changed into DCE, finally to vinyl chloride, and then eventually ethene, this harmless byproduct. Now, during this process, everybody's always concerned about, please don't turn my TCE problem into a vinyl chloride problem, because these daughter products are actually more toxic and more mobile. This often can happen if you are applying an electron donor that isn't appropriately soluble. And I'm going to walk you through that as part of the next few slides. In terms of what you can expect to see, this is kind of a textbook reductive dechlorination process. You see a drop in these parent compounds, PCE and TCE, subsequent peaks in DCE and vinyl chloride, and then eventually through to ethene production. Now, we in Regenesis, what we do is we research, develop, and commercialize these injectable substrates. So everything that we use and we recommend has been engineered to clean up groundwater. And there's 4 sort of cornerstones, if you like, as to how these injectable substrates need to perform. So first and foremost, they need to be easy to use. There's no point having a product that you're going to deploy on a site if it's a nightmare to try and use and get into the ground, or if it's very unsafe to handle. The second 3, distribution, is also important. If you're injecting something into the ground and it doesn't travel more than 30 centimeters from your injection point, means you're going to need a lot of injection points. It means you're going to need a lot of injection points, and the cost of that remediation is going to go up. Now, particularly for electron donors, appropriate solubility is important, and this is where persistence and reactivity come into play. So when I mean an appropriately soluble electron donor, what I mean is you don't want to inject something into the ground such as lactate, which once injected releases hydrogen very quickly, but also washes away. So it isn't particularly persistent, but it is very reactive. The flip side of that, something like vegetable oil, you'd inject that into the subsurface, it would stick, so it's not going to wash away, but the fermentation process may be much slower, so it's not as reactive. So you want something that's appropriately soluble, that's persistent, that will release hydrogen in a controlled fashion to create a stable environment over a long period of time. So you grow a large microbial consortia to ensure that you can break down as much of your contaminant mass as possible. And if you can add enough hydrogen, create a stable environment for a long period of time, you can deal with DNAPL concentrations of chlorinated solvents in situ. So to do this, we've essentially invented a molecule called 3DME. The 3D stands for 3 electron donors. It widely propagates in the subsurface. It essentially forms a series of micelles that can self-distribute in the aquifer. We've done sites where we've injected it on 10-meter centers to greatly cut down on program time and site time on site. The idea is that it's a single injection, so one injection will produce hydrogen for about 5 years. That doesn't mean it's going to take 5 years to clean up your site. It just means that it will continue to work for up to 5 years. And it provides an immediate, mid-range, and long-term controlled release of organic acids that will subsequently ferment into hydrogen to drive that reductive dechlorination process. In terms of what this molecule looks like, it's a lactic acid tetramer. It's actually an evolution of a previous product called HRC, our hydrogen releasing compound, where we have an ester bond and then fatty acids stuck onto the side. This creates a polar molecule that can essentially paint the subsurface with electron donor. Once in there, a series of electron donors are released, lactates, polylactic esters, and then finally fatty acids, etc. How it works, so once it's injected into your aquifer, the product starts to dissolve. And as it dissolves, it releases a series of organic acids, lactic acids, pyruvic acids, etc. And then a different group of microbes take over and they start to ferment these acids. And as these acids are fermented, hydrogen is released. That hydrogen then acts as an electron donor. It's utilized by these dehalogenating bacteria to swap out these chlorine atoms for hydrogen atoms, driving that reductive dechlorination process. And because you have this long-term release of hydrogen, you get full dechlorination right the way through to ethene. We also added an inoculum with this. So as I said before, right at the beginning of the presentation, chlorinated alkanes. So we had a TCA plume here. Often if you rely on native microbial consortia, they will eventually get to degrading the TCA and DCA, but it may take a little bit of time. And here we had some time pressures. The American parent wanted to see significant reduction in a very short period of time so that the liability could get signed off. So here we also added an inoculum of D-halicocoides bacteria to expedite the TCA and DCA degradation. In terms of the activities on site, so we did an initial pilot trial. Now, when we looked at the conceptual site model of the site, there wasn't much that worried us in terms of the geology, in terms of the levels of contamination we had on site. But there was a concern that during the MIP trials, it was understood that they struggled to get their MIP rods down to the required depth. So there was a worry that, okay, if we go down the direct push injection route, which is much cheaper, you don't have to install dedicated injection wells. There's no infrastructure left after the injection works have been completed. Would we be able to get to the required depth? So we did a small trial around one of the more problem wells, borehole 110. We successfully reached below 9 meters. We successfully reached 9 meters below ground level. So we proved the efficacy of the direct push injection. We did inject the product, so we did inject 3-DME with the inoculum. And then as a sort of a secondary line of evidence, if you like, we did see reductive dechlorination starting to take place. You can see TCE levels immediately after the injection sort of jumped up a bit. That's down to disturbance from injecting this fluid. This then dropped off, and you can subsequently see the buildup of the daughter product, DCE, that would suggest that the reductive dechlorination process is well underway. I'm not sure if everybody else can see that, but there is actually a slight blue line right at the top of the last column. That's actually vinyl ethene production, rather. In terms of the full-scale works then, so this comprised injecting 60 direct push injection points across this 1,500 square meter area. These injection works were done overnight and on weekends as to not disrupt the commercial operations on the site. In total, we spent 2 weeks, maybe just under 2 weeks, completing these injection works. And then once we demobilized from site, you had continual release of hydrogen, remediation was ongoing, and then all the environmental consultant had to do was monitor. So it was a one hit, then people could continue to monitor for the required period, and there was no ongoing disruption, no excavation was required. We were just injecting and applying this product into the ground. In terms of our results, so we did the initial injection and we saw some pretty significant disturbance. So you can see here we hit at one point total over 100,000 micrograms per liter of chlorinated solvents. Again, very much down to disturbance. This indicated to us that there was some significant contaminant mass there. This quickly reduced though, so you can see by month 7, things had calmed down a little bit. By the final 3 monitoring rounds, you can see that the TCE levels had continued to drop, and we did see some ethene production that would suggest that we were getting full dechlorination on this site. Crucially, and this was the requirement in the contract, is that we saw between a 98 and 99% reduction in contaminant levels of and TCE respectively, that enabled the American parent to then tick the box to say that they'd done what they said they were going to do as part of the contract. As I say, similar story for the TCA, so dealing with some pretty significant levels of TCA here. You're then seeing dechlorination of the TCA in the last 3 monitoring rounds, also indicating full dechlorination with the production of ethane. So in conclusion then, what we find is, in terms of our work in Regenesis, probably about 65% of our sites tend to be commercially active sites that require some sort of remediation. Just because that site is commercially active, that doesn't necessarily mean that the remediation cannot take place. What we find is, though, that communicating to the occupants their expectations, expectations of reduction, expectations of actually what's going to happen on site is key. Often, by day 2, they understand that actually it's a fairly small rig that's going to be taking up quite a small footprint of their site to do these application works. And crucially, and it's something that we see all the time across many sites, it is absolutely possible to through enhanced biological remediation to address DNAPL concentrations of chlorinated solvents in situ. And yeah, that's everything. Thank you for listening, and any questions?
Brilliant, thank you, Jack. That was really interesting. We slightly lost your audio on slide 35 when you were starting to explain your results.
Right.
Do you mind just really briefly summarising that slide only? Because we lost you very slightly at the beginning of it.
That's okay.
For those who may have questions.
No problems. If we just go back one. So, so this is post-injection after the full-scale application works. You can see 4 months after injection, there was a significant jump in contaminant levels. This is largely down to disturbance from injecting quite a high volume of liquid into the aquifer. Fairly quickly afterwards, those levels were reduced. Then if you look at the final 3 monitoring rounds, you can see that the TCE levels continue to drop, and there's clear evidence that reductive dechlorination is occurring. We actually reduced TCA and TCA levels by 98 and 99% respectively across the site. Again, similar evidence with the TCA, so we got co-degradation of these 2 groups of chlorinated solvents, showing that reduction in the parent compound and then a subsequent production in daughter compounds, and then including ethene production, which would indicate that you had full dechlorination occurring.
Perfect.
Okay?
Thank you very much.
Right.
Yeah, that's
no
perfect.
worries.
We just lost you very slightly, so
okay.
Yeah, just to fill in any gaps. Okay, so we've had a couple of questions come through. So Richard Anderson, he's asking if there's any evidence or case studies, examples of success with PCB containing oil contamination.
We wouldn't. We've not done sites using enhanced reductive dechlorination with PCBs. PCBs are a tricky contaminant to address. Something that we absolutely wouldn't recommend is chemical oxidation, because what you can end up doing is creating a much worse problem than that you would have started with. So no, we typically wouldn't recommend the addition of a electron donor for PCB remediation.
Okay. Anywhere that you would direct people to look into that?
I think physical abstraction is probably what you're left with, and maybe some sort of stabilization technique as well. The thing with PCBs is that they don't really want to. They're not particularly soluble. They don't want to be in the groundwater. So often there isn't a pathway. So really, you're more often than not dealing with a soils problem rather than a groundwater problem.
Got you. Okay. Yeah. Okay. Brilliant. The next question is from Dan Mayer, and he said, "What happened to the chlorine liberated from the TCE, PCE, VC?"
I think it's generally precipitated out as a salt, but I'd have to double check that.
Okay.
Question.
Perfect. If that's a conversation that you want to have a bit further with Jack, Dan, I recommend getting in touch with him. Details are at the end of this presentation. I can pop them on the screen now for you there as well.
No problem.
So Cheryl Donahue has also said, "What is the 75% of the original average concentration, and how did the increase in COC levels affect the results of the contractual percentage? Was the risk to achieving the targets?"
What was the 75? What is the risk in achieving the targets? In terms of I'd need to be reminded contractually of exactly what was in the wording. They were looking at 75% of the baseline that was taken over about 3 years. And what we were able to do was reduce it to below that 75% mark. But crucially, what they saw was no rebound during this monitoring period. And that was enough to relinquish the liability. And that was the objective that was required. I think if we were dealing with a more high risk site, if I'm honest with you, I think if we were dealing with a more high risk site where there was a risk to controlled waters or human health, then probably more monitoring would have been done beyond the 16-month period.
Got you. Okay. Sam Brofton has also asked you, was ground gas monitored during the monitoring period of this particular site?
I don't believe it was. The buildings on the site were sort of large warehouses that were open air. All the injection works weren't done in the buildings, and there wasn't evidence from the SI that there was much contamination under the building. It was all mostly within the yard area. The source was thought to have been an interceptor in the yard area. Okay, that makes sense.
Mm-hmm. And Connor has asked you, would there be any environmental conditions in the subsurface which may hinder the performance of the injected molecule?
Yes, that's a great question. So we have a series of different electron donors that we can use. So if we were dealing with a pure clay, for example, 3-DME is quite a high volume product to inject into the ground. So it needs to be fairly permeable to get these large volumes in. If you were dealing with a pure clay, we could use something called HRC, which is a much more highly viscous product. It's more like honey. So you're injecting a much lower volume, but actually a higher concentration of donor. In terms of, from a geochemical point of view, when we design these jobs, we always look for competing electron acceptors. So something here in the UK is high sulfate levels. Essentially, these Dehalobacter bacteria, they want to, the ideal redox conditions are sort of just below sulfate reducing conditions. So where you have lots of sulfate in the groundwater, we would account for that in the design. We would call that a competing electron acceptor. And then we would need to ensure that we have enough hydrogen to sort of overcome that obstacle to then ensure that reductive dechlorination can happen. Okay.
And when taking into account the two different products that you could inject, are there any other considerations that you need to take on board? Is there a considerable price difference or setup cost or anything like that?
It varies between sites.
Sure.
There can be. 3-DME is certainly a more cost-effective option because it distributes so widely. It means that you need far less injection points. So your total project cost. So if you take out, when I say total project costs, I mean application costs and the technology cost is often much lower. Whereas if you're injecting something like HRC, you need far more injection points, so your time on site's much longer, so then that can have an impact on cost. But then in saying that, if you're using HRC and you're dealing with something that's fairly low permeability, you might be dealing with quite a small area, so that cost may not actually be that great.
Sure, okay, so they'll peak and drop. Brilliant. All right, well, that's all the questions that we've had in so far. If there's any others, please do feel free to submit them now. If not, Jack's contacts are at the bottom of the presentation, so you can contact him if you need to. For those who have logged in, thank you. Please make sure that you record this on the IES CPD tool on the members area of the website. If you've got any problems accessing that, do contact the project office and we can do that for you. This webinar has been recorded and it will be put on our YouTube channel for you to access and share around with colleagues and your wider networks. So do follow us on YouTube. You'll also be notified every time a new webinar goes up there in case you've missed the live version. But do take a note of Jack's contact details if you want to get back in touch. And if you've got any more questions for us, then do let us know. But in the meantime, thank you very much, Jack, for presenting. That was really interesting. And yeah, hope something will come of that.
Sure.
Brilliant.
Yeah, thank you, everyone, for listening.
Brilliant. Thank you very much.